The future of embedded systems is being reshaped by artificial intelligence. Imagine working in an environment where multiple AI models like GPT 4.1, Claude, and Gemini collaborate seamlessly within your IDE. Privacy concerns fade with offline local models, while retrieval augmented generation injects rich, project-specific context into every suggestion. AI agents can now brainstorm, write, debug, and test code in real time together. This isn't just about faster coding, it's about smarter, safer, and more innovative development workflows. In this lesson, we'll explore the trends and tools defining the next decade of AI-powered embedded engineering. Future AI-assisted embedded development environments won't rely on a single model, but instead offer a multi-model ecosystem. Imagine having GPT 4.1 for deep reasoning, Claude for structured documentation, and Gemini for real-time optimization, all accessible within one IDE. This collaborative model approach allows engineers to switch or combine AI expertise depending on the task. Local and offline models are gaining traction as privacy and latency become critical concerns. Running AI inference directly on your workstation or edge server ensures sensitive code never leaves your environment while cutting down response times significantly. Retrieval augmented generation, RAG, is another emerging trend, giving AI agents the ability to pull relevant project documentation, data sheets, and prior commits into their reasoning process. This makes their suggestions highly contextual and tailored to your specific hardware and constraints. The future of embedded engineering is moving towards real-time multi-agent collaboration, where several AI tools work together, one writing code, another verifying safety, a third optimizing for performance, while you, the human engineer, remain the final decision maker steering the project. Starting a project in the future could mean skipping hours of manual preparation. AI will automatically generate requirements documents, user stories, and design specifications based on your high-level goals. These drafts won't just be plain text. They'll include automated diagrams such as mermaid flowcharts showing data flows, state machines, or task scheduling visuals to help teams understand complex systems at a glance. AI agents will coordinate the initial planning phase, proposing structured test plans and verification strategies upfront to catch issues earlier. Multiple specialized agents will divide responsibilities, one drafting firmware drivers, another writing unit tests, another managing optimization parameters, ensuring that every aspect of the project progresses simultaneously. Project managers can rely on these tools to auto-generate prioritized task lists, assign effort estimates, and flag potential dependencies between features. The result is a smoother transition from concept to execution, letting engineers focus on refining designs rather than getting bogged down in administrative tasks. The hardware side of embedded systems is evolving to complement these AI workflows. Many new microcontrollers and SoCs now ship with dedicated machine learning accelerators, or neural processing units, NPUs, enabling efficient edge AI inference without draining system resources. This allows real-time decision-making, image recognition, or anomaly detection right on the device, reducing reliance on cloud compute and improving reliability in low connectivity environments. AI-powered tools will also change how firmware is written. Instead of crafting every routine manually, engineers can describe desired behaviors in plain language, and the assistant will generate optimized code tailored for the specific microcontroller's capabilities. Choosing the right hardware will increasingly depend on AI compatibility, from supported toolchains to available accelerators. Performance tuning will remain a human skill, balancing compute power, memory allocation, and energy efficiency. Future workflows will combine AI-driven suggestions with expert fine-tuning, ensuring that devices meet stringent real-world constraints while pushing the limits of embedded intelligence. This course has guided you through foundational concepts of AI in embedded engineering, building layer by layer toward more advanced techniques. We started with the basics of AI agents and prompt engineering, explored automated workflows, debugging, and tool integrations, and emphasized responsible, ethical AI use. As we look toward the future, embedded engineers will increasingly rely on multimodal AI agents, real-time collaboration, and intelligent code generation, transforming how firmware is conceived and deployed. Every lesson you've learned here, from clear prompt design to human oversight, sets the groundwork for thriving in this evolving environment. The next era of embedded development won't eliminate engineers. It will empower them to innovate faster, handle complexity with confidence, and unlock features previously considered out of reach due to time or resource constraints. While AI tools will become more powerful and autonomous, the human role in validation, safety, and ethical decision-making will only grow in importance. The future demands not just skilled engineers, but thoughtful ones who document workflows, maintain transparency, and ensure traceability in every AI-assisted decision. Precision prompting and structured requests will remain essential to guide AI effectively in large, multi-agent systems. Choosing the right tools for your ecosystem, whether local models for privacy or cloud tools for scalability, will become a strategic engineering decision. Ultimately, the most future-ready engineers will combine technical expertise, creativity, and responsible AI usage, adapting workflows as new capabilities emerge while holding safety and accountability as non-negotiable standards. Staying ahead in this rapidly evolving field means continuous learning and experimentation. Start by exploring documentation for tools like Cursor, Copilot, JetBrains AI, and IntelliCode to deepen your understanding of current capabilities. Practice reading datasheets and application notes using assistants like ChatPDF, building your skill in querying and contextualizing hardware data effectively. Join forums, online communities, and Discord channels where other developers share real-world experiences integrating AI into embedded workflows. These spaces are invaluable for troubleshooting, discovering new tools, and gaining insights from cutting-edge projects. Finally, experiment with small-scale hobby projects, applying AI tools in safe, low-risk environments. The more you practice, the more intuitive AI-augmented engineering will become, preparing you for future industrial applications. AI is transforming embedded development, making workflows faster, smarter, and more efficient. But here's the real takeaway. AI is not here to replace human expertise. It thrives alongside it. The skills you've learned in this course, prompt engineering, multi-tool workflows, responsible AI practices, position you to leverage AI as a true partner in engineering. With it, you can automate repetitive tasks, catch bugs earlier, and free up time for the creative, high-level problem-solving that only you can do. The future of embedded systems is AI-augmented engineering, where human decision-making and artificial intelligence work hand in hand to build safer, more reliable, and innovative solutions. So keep experimenting, keep refining your workflows, stay curious and intentional about how you use these tools, because the engineers who will lead this next era won't just know how to code, they'll know how to collaborate with AI wisely. Thank you for joining this course. I hope you leave not just with new skills, but with a new way of thinking about the future of embedded engineering.